Good morning. Welcome to this last session of this conference. We have two talks today, and I'm happy to introduce our first speaker, Professor Eswara Rao from the Tata Institute of Fundamental Research. And his talk is going to be a survey of toroidal algebras, toroidal Lie algebras and Witt algebras.
So thank you, Raghavan, Professor Raghavan, for the introduction. I also record my thanks to the organizers who made this visit possible. Okay, so I'll be talking about two Lie algebras. One is toroidal Lie algebra, which is a generalization of affine Cox-Miller Lie algebra, and another is the Witt algebra, which is a generalization of Virasoro algebra. So I need to fix the notation, very short notation. Okay. Z plus. Okay. And AN, which is also generally denoted by A for the time being. The Laurent polynomial algebra in n commuting variables. Okay. So R belongs to Zn, and T power R is equal to belongs to A. Okay. Now I will define an abstract set omega A. This is span of T power R Ki, where R runs from Zn and I runs from 1 to n. Just symbols. You just take a space, vector space, spanned by these symbols, and there is a relation and where our interest is in this space. This is the space we are interested, and you can easily check infinity if n is greater than or equal to 2, and E is 1 if n is equal to 1. One can check this. Okay. Now let G equals be simple Lie algebra, finite dimensional, or complex numbers. Okay. Now I will define a Lie algebra. This is one we have seen it in earlier lectures, and I will add a center. I will also add a D. These are derivations, 0-degree derivations. And this is a Lie algebra. You will see why it's a Lie algebra. B, non-degenerate, invariant form on G. And also I will use a notation for Lie bracket. just the usual leaf bracket plus that's the leaf bracket, and the D, and this is central. And the D is actually measures the gradation. These are all graded by Zl. So just the measures the gradation. Between them, there is no commutator. That's the Lie algebra. And one knows I will give a name to this Lie algebra. If you just forget DIs for some time, it's actually a central extension. So, universal. Of G tends to A. This is a known result. We don't need it. It's a known result. We don't need to. What happened? Some resound is coming? So, our aim is to study E modules. Okay. So, among them, there is something called integral module. These are more reasonably accessible modules. So, we start with this. Okay. So, let us call it V. So, what's the definition? Given V in V, X alpha and Z alpha, G alpha, root system, and M in Zn, there exists N, such N, which depends upon V alpha and M, such that so this is the definition of integral models, and we will classify certain models. We classify irreducible, integral, modules for tau bar. That's our aim. So I will give one example. Simple example this is. The case acts trivially. Okay, let's see. First thing is, so let M1, Mk be maximal ideals of A. This K and that N are independent. K could be anything and N could be anything. Okay. Now by Chinese remainder theorem, we see that it's surjective map. Okay. But you see, A is finally generated, this is a maximal ideal, so the quotient is a field. So it's easy to see that this is actually T. and k copies of C. Okay. Now we will do a little different. So look at you tensor with A. So when you tensor with A, it's actually G, k copies. So there is a subjective map from here to here. This is what we all call evaluation model, evaluation map. So now take irreducible finite dimensional module for G, say Vi. Okay, so Vi means 1 less than or equal to I less than or equal to K. So look at V, which is, so each Vi is a G module, and the tensor product becomes a module for this Lie algebra. Each Vi being irreducible, this will be irreducible for this. So you just lift it. So what we have? So that gives an irreducible model for this. Problem? D does not act on V. So that can be rectified. So what you do is you, okay. So consider V tensor A. Now this becomes infinite dimensional. Anyhow, this being finite dimensional, anyhow it's integrable, and this will be also integrable. So how do you define a module structure? Equal to XOR V. This makes sense in V. So that's the definition. So you have a non-graded module, and by tensoring with A, you get a graded module. Problem is, not irreducible. So, but completely irreducible. Completely irreducible. Whose components are isomorphic. Up to a grade shift. Okay. So we have a class of modules with some nice properties. It's an integral module, and you give an irreducible integral module with finite dimensional weight spaces. So now let us take the second case. Sorry. So example 2. The case is this is omega by dA acts non-trivial. Okay. For that I need some notation. You look at G, L, and Z. Let me call it simply G. These are n by n integral matrices whose determinant plus or minus 1. It's a group. Now, G acts on A. So you take a B belongs to G, And B tends to T power R is nothing but T power BR. So let us say E1, E2n basis for Zn, and also I need this notation, the a form on Cn. There is Ei, Ej is equal to delta Ij. That form is needed. So you just put Si is equal to T power B Ei. And notice that Laurent polynomial in these many variables is actually, this is what we call choosing the proper coordinates. Okay. Now, G, which is GL and Z, acts on tau bar. Okay, let us see how it acts. So B XR is equal to XBR, as simple as that. I need small notation. So B acts on this also. B also acts on D, which I will not which I will not indicate now, but I will do it little later, in more general form. So, okay, now you have this 0-degree center operators. There is an infinite set, but 0-degree center operators are finite. So they are actually K1, Kn. So using affine theory, we see that each Ki acts as integers, an integral model, not otherwise. Model. Okay. Now, how does the B act on this? B, let us say, is usual multiplication. Okay. Now, as I said, each of them will act by integers. So you have a B and you have a set of integers. But you see, it's a standard fact that given a set of integers and you can find a B, that this is equal to, in fact, greater than 0, like that. So this is a really great reduction. Because of this, things will be much better. Okay. So, given any integrable module, I can twist with GL and Z and make it like this. Okay. So, example 2. Okay. So, let us take a map. For that, there's something else I have to do. This is affine Lie algebra with the first variable and a center. Okay. Now, look at this. And map it to one variable less. So how do you do this? You take extensor T power R, send it to extensor T1 power R1, tensor with e power r prime, where r prime is from R2 onwards. Okay. And how the center goes? So look at this. It goes to K1. There is a K1 here. Tensor T power R m prime, where m1 is 0 and I is equal to 1. Okay. Our other center is sent to 0. So now the situation is similar to the earlier case. You have a GFI, you have this, and you can get a surjective map. Okay. So now what you do is you take V lambda I, V highest weight integral module for GF. And look at and lift it to this. You get a module, but now the center won't act trivially, it acts non-trivially, but only this part. Okay. So one may wonder, this map is too nice so that you are getting modules, but it is in general true. I will tell you what it is. So suppose you take an irreducible model without any assumption of integrability, any irreducible model. Okay. Anyhow, I need, sorry, I need to do something more. So you have two class of modules. One is center zero, other is non-zero center, non-zero center. Okay, let me state the theorem first. Wait. Yeah, that's what. Now you tensor with this. The derivations, the part of the derivation is only to the measure of the gradation. If you are here, there is no ds action. But if you do this, V tensor A and like this, then ds will act. But unfortunately, the module itself is not irreducible, but it's completely reducible. Okay. Now theorem. Suppose V is irreducible, integral with finite weight spaces. Finite weight spaces is very important. Finite weight spaces means your G tensor A is one way it's graded by lambda and also graded. The gradation is this, delta in both. Then V comes from example 1 or example 2 up to twist of GL and Z. See? But you see, the integral models in the affine case are very important. It has a character formula and so much work has been done. Slowly that chapter is over and people are going to different kind of models. But integral models are really very exciting. It has a nice character formula and it's inherent under the Weyl group. But here, they are not so interesting. Reviewer wrote, it's disappointing result. Yeah, but what can we do? They don't exist. Okay, but you see, okay, integral models are not so great. What about any irreducible model? With finite dimensional weight spaces. Okay. I wrote there, but I will again write here. So I have given a map. Given any irreducible model with finite weight spaces, you can choose coordinates in such a way that it factors this. So the kernel is central, the kernel here, it vanishes, this kernel vanishes. So it's in general. So classification of irreducible module is reduced to this. Okay. Now we make one remark. So GF tensor an minus 1. Center is here. I will call it D1. That is here. It acts here. And other D2, Dn. Okay. Now there is a 1-1 correspondence. So given an irreducible model with finite weight spaces only for D1, you get a model here, and given a model here, you get a model here. So to classify irreducible model with finite weight spaces for toroidal algebra is nothing but classifying models for this. But that is an open problem. Nothing has been done up to now. Okay. And I will tell you one more thing. Okay, there is time. See, the finite dimensional weight space is very important. Without finite dimensional weight space, we can't do anything much. Now, the center, yeah, it's an open problem. See, integrable models are not so exciting. That has been done. Now, the next thing is, what are all the irreducible models? Any irreducible model goes model this. So, it is a module for this Lie algebra and this derivation. Now, one can prove that there is a 1-1 correspondence between this and this. The difference is, here the weight spaces are finite dimensional with respect to only D1 and delta. Here much bigger. But there is a 1-1 correspondence. You can go from here to there and from there to here. So the question is, what are all the irreducible models for this Lie algebra with finite dimensional weight spaces? That's the question. Up to now, we don't have any problems. Okay. Now, as I told you, this central action and finite dimensional weight spaces are somehow linked. I will give you one example to make you understand what it is. Okay. So you consider a slightly smaller algebra, G tensor A and a D also. Okay. Now, So this is a much simpler algebra, and people thought in the beginning that rather than considering such a complex real algebra, why don't we do it here? Maybe this is more general, more suitable generalization. Okay. So this is a finite center. Now, not only that, they constructed models with using some high-tech methods, but all those models have infinite dimensional weight spaces. And from my theory, it follows that there are no models for this real algebra with this section non-trivial. There are no models. There are no models with finite dimensional weight spaces where kx trivial, non-trivial. That's done. Okay. Now we will go to Witt algebras. Witt algebras. That is, I will denote it by derivative. Set of all derivations. On A. Okay. Now, one of them is, so I will denote di to be ti dou dti. Now, if you look at t power r di acting on t power s is actually si t power r plus s. So, I will give you a better notation. dur is equal to sigma ui t power r dA. Now, in this notation, it is easy to state a leaf bracket. Yeah, that's a leaf bracket. It's known to be simple. Yeah. So, what are the modules for this? So, one thing is del A is centrally closed. No central extensions. It is true. This result came from some physics people long back, but it has an abelian extension, which maybe if time permits, I will come to that. I don't have much time, I think. Okay. Now, modules. But 16 means what? 16 minutes are over, or what is the systems left? Left, okay. So, I got this model from a physicist, Larsen, but it's also done by Chen, the Larsen-Chen model. So, let V lambda be finite dimensional, irreducible module for GLNC. You know GLNC, right? This is span of these matrices. Okay. Now this lambda is dominant integer for SLNC. GLNC is what? SLNC less an identity operator. So lambda is dominant integral for this, and identity acts by B. So the module is, and I also take alpha in Cn. F alpha lambda B equals V lambda B tensor A. Okay. So let us write down the action. DUR acting on V tensor T power R equals E power, let us say S, U S plus alpha, this is the bracket in Cn, V tensor T power R plus S, less sigma Ui Rj and Eji will come here at V. This is in the V and you tensor with T power R plus S. So this is this module came from a physicist. So what are its properties? So theorem, F alpha lambda beta is irreducible for der A unless lambda B equals, I will tell you what it is, delta k R 0 B. And delta k is actually minuscule weights. Minuscule weights. Those who know it will know minuscule weights. Okay. Now you take V to be Cn B natural GLN model. Then what we know is V is equal to V delta 1 and also you take kth V, kth exterior product, and this is known to be equal to V delta K. So the module is reducible only in this setup. And moreover, so it's irreducible most often. Very few cases it's reducible. There is only one proper submodule up to a trivial factor. Okay. Okay. And so F alpha delta k has only one proper submodule. Up to trivial factor. And that trivial factor occurs only when alpha is in Zn. And one more thing, I took alpha in Cn, but what exactly is it? Okay. So if two alphas differ by an integral point, then they are isomorphic. One can reorder the gradation. If that is done, so let's come to end. A Derrière module is called jet module if AX and associative. That is, T power R, T power S is actually acts as T power R plus S and T power not acts as 1. See, when you take a module for Derrière and A, this is not automatic because this is only associative product. A as a Lie algebra is trivial. This won't follow, you have to assume it. Now, look at F alpha lambda B, which is E lambda B tensor A. And this is a jet module. Because T power R acting on V tensor T power S, actually V tensor T power R plus S. So as a jet module, it's always irreducible. Even this exceptional case also, it becomes irreducible. Now the theorem. Suppose V is a jet module with finite weight spaces. With finite dimensional weight spaces. Then V is isomorphic to F alpha lambda B. Okay. Any jet module with finite weight spaces is isomorphic to Larson chain module. Okay. Now, that's the last bit. Okay. Now, we have a lot of modules here. Some of them are reducible. Okay. Now, while writing a expository article, I wrote, it will be nice if these are the only modules for Derrière. And that turned out to be a conjecture for some people. And that conjecture has been solved very recently by Pitorni and Billig. But it's highly non-trivial solution, and it was open for some 8 to 9 years. Okay, so just indicate what it is. You start with a Derrière module, and you construct another Derrière module, which is also a jet module, but it has finite weight spaces, and there is a surjective map. This is what they did. So they produced a jet module with a surjective map to the given module. But we know all the jet modules. Also, we know all the submodules. Submodules and quotients, you know. So conjecture is solved. So what does the conjecture say? Any Derrière module comes from here only. It comes from here only. And even for n is equal to 1 case, n is equal to 1 case, it's a conjecture by Cox. And it stood ground for 8 to 9 years. And eventually Matthew proved. And also I had to indicate that in the conjecture for n variables, they used this. Without this, they can't prove that. Okay, I'm also a little tired. Okay then.
We have time for questions.
Modules.
This module, jet module.
So they like what Futani and
Given a module V, they produce another module, which is a jet module with finite weight spaces. You start with a module with finite weight spaces. But this is a jet module. It need not be irreducible. They couldn't prove that it's irreducible. It's a jet module with finite weight spaces. Okay? Okay, new. sorry. This is what they proved. From this it will follow. See, this V will have something like this, a filtration. The successive models are jet models. So at some point, this gives a non-zero map. I'm a little sorry, but in a sense, they proved it's irreducible also. So once it's irreducible jet model, we know what they are. And we know what are its quotients. So problem solved.
Any other questions? Not, let's thank Professor Raghavan.